Okay, so we're going to continue on from where we left off yesterday, looking at some of the Chapter 17 homework solutions that you had requested. And so 13A was requested. And so here's the graph of y equals 1 over 1 plus cosine x. The first task that we have to do is to show that the derivative of sine x over 1 plus cosine x actually equals 1 over 1 plus cosine x. And so we'll take the derivative of that, and we'll use the quotient rule. So the derivative of sine x is cosine x, and we multiply that by the denominator, which is 1 plus cosine x. And then we leave the sine x. We have to subtract as part of the quotient rule. We leave this sine x as it is here, and then we take the derivative of 1 plus cosine x, which is negative sine x. And then we take the denominator and we square it. Then we're going to use the distributive property and expand this in. So that's how we get the cosine x plus cosine squared x. And we multiply these two together to get plus sine squared x. So if we were to group these two together, that actually equals 1. That's the the Pythagorean identity. And so that equals 1. And this cosine x comes over here. And that just matches up with the denominator. And so we've got 1 plus cosine x over 2 of these 1 plus cosine x's. And this one, this whole thing will cancel out with one of those. So we're left with 1 over 1 plus cosine x. So now the reason why we had to differentiate this in order to find this function is to show that if we were to now integrate this, we would then get this sine x over 1 plus cosine x. And that will be a lot easier to evaluate when we're trying to find the area. So if we go ahead and try to find the area here, we're going to, we're going to integrate this to get that. So this is kind of showing us what the integration is if we don't know how to integrate this thing in the first place. So for 13b, when we're trying to find the area, we're going to integrate 1 over 1 plus cosine x dx from 0 to 2. And this integral we now know is sine x over 1 plus cosine x. And we're evaluating that from 0 to 2. And okay. And so then we're just going to substitute these values in. So we'll have sine of 2 over 1 plus cosine of 2 minus sine of 0 over 1 plus cosine of 0. And so sine of 0 is just 0, because if we have the sine curve, we see that normal sine curve for the parent function just looks like that. So this whole thing goes to 0. And so we're left with sine 2 over 1 plus cosine 2. So we'll have to check that out. Those would be, of course, in radian measures. And so if I can just do that, make sure that my calculator is in radian mode, which it is. So I've got sine of 2 divided by 1 plus cosine 2. And we get 1.557, or approximately equal to 1.56 square units. Okay, and so that's that question, number 13. And we move along now to section 17C. We'll look at question 7. This is a cross-section of a roof gutter, so an eaves trough, and it is in this shape. Love how they come up with these functions for these questions. making them real world problems. And so the function is 0.024, blah, 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 all this, and from -5 to 5. So we're going to find the cross-sectional area of this. So that means that we're going to determine the integral and evaluate it from -5 to 5. Since this is below the x-axis, we're going to stick a negative on there, because we know that if the area is below the x-axis, it's going to be negative. And then we integrate this. When we do that, obviously the exponent 4 goes up to 5, and then we divide this by 5, and that's going to give us 0.004. This exponent is going to go up to 3, and then we divide this by 3, so that's how we get this coefficient here. And then we just stick on an x for that 2.5 there. And we evaluate from -5 to 5. And so when all this is said and done, you substitute 5 into here, 5 to the power 5 multiplied by 0.004. Apparently is going to give us 16 2/3. No, sorry, not specifically. When we evaluate all this, we substitute 5 in here, we substitute 5 in here. All of that is going to give us -16 2/3. And then we substitute -5 into all of this, and we're subtracting. This subtraction symbol is actually for the operation of fundamental theorem of calculus, f of b minus f of a. This is that minus sign between the two. And so the f of a part is 16 2/3, and we subtract them, we get -33 1/3. And of course, because of that negative out front, it changes this to positive. Okay, so then the cross-sectional area of this is 33 1/3 square centimeters. And if we want to find now the volume, well, for any sort of volume of a prism, it's just the area of the base multiplied by the length. And the area of the base, so this is the base, that cross-sectional area that we're just talking about. And then we multiply by the base or the length, and the length they're saying is 20 meters. So we'll see how much water that can hold. And so there's the area of the cross section multiplied by the length of the gutter. So here's the area of the base, which I was mentioning before, and the length. And so 33 1/3 square centimeters multiplied by 20 meters. Well, we have to convert that into centimeters to have the same units, and that becomes 2,000 centimeters. And we multiply those, we get 66,666 2/3 centimeters cubed. And from perhaps work in chemistry, you might notice or know that 1 centimeter cubed is 1 milliliter. So this is a quick conversion into milliliters. And then we would just divide that by 1,000 to get it into 1 liter. And we get 66.7 liters approximately of water that can be held in this rain gutter. Okay, so that's that question finished off here. And we'll go to question 8a from the same section. We need to find the integral of x squared cosine x cubed dx, and this is that function. And after we do that, we have to show that the red shaded region is twice as large as the blue shaded region. So this red here, twice as large as that in terms of area. So we look at the integral that we have to find, and the main part of this is this. So if we were to take the derivative of this function, we would get negative sine x cubed multiplied by 3x squared. So when we take the derivative of the angle, that x cubed, it becomes 3x squared. Well, here's that x squared part right here, but there's no 3 in front of it. So what we have to do is we have to, well, it's just 1 in front of there right now. So another way we can write 1 is we can write 3 over 3. And so if we stick a 3 in there and then we multiply by 1/3, that gives us that 1 coefficient of the x squared. And now we've got that 3x squared here. That would come out if we took the derivative of x cubed of that angle. So now we're ready to use substitution. So we're going to let u equal x cubed, so we can replace this x cubed with u. And then we'll take the derivative of this. So du by dx is 3x squared. So then we can rearrange this. We can multiply this dx to both sides. So we'd have du equals 3x squared dx. And then we divide both sides by 3x squared. And so that means that then on this side, this goes, and we're just left with dx. And we can replace dx here, or here, whichever, with this thing. And then that 3x that's down here, replace it, or we'll cancel it with that 3x squared. And then we're just left with, well, of course, the way the textbook has done it, where they've got du by dx, they cancel out the dx's in that way. But the way we've done it in the past, we would replace this dx with this du over 3x squared. The du is now in here, and the 3x squared cancels with that 3x squared. So we're now integrating cosine u du. And the integral of cosine u is sine u. We've got that 1/3 still out front, and then plus c. Okay, and then we'll just substitute this x cubed back into the integral, and we're all set to go. Okay, so that's that first part. So now we know the integral, so we'll be able to do some area calculations here. Now we see up here in this function that it has an x-intercept of 0, and then it's got another x-intercept there and there, which we don't know yet. So we know it has x-intercepts when y equals 0, so we set this equal to 0, which we have here. And then that means that either x squared equals 0, which we already know, or cosine x cubed equals 0. So of course we know that x equals 0, and we're looking for the two smallest positive x-intercepts, and they occur when x cubed equals pi by 2 or 3 pi by 2, because if you look at the cosine curve looks like this. This is pi by 2, and this is 3 pi by 2. And so then x cubed will equal, so that's where we'd substitute in the pi by 2. So cosine of pi by 2 equals 0, and cosine of 3 pi by 2 equals 0. So that means that x cubed will equal pi by 2 or 3 pi by 2. And so then we just take the cube root of both sides. And so then the cube root of x cubed is just x. And the cube root of pi by 2 is the cube root of pi by 2. And again, the cube root of 3 pi by 2 is the other one. So x equals these values. So we now have values. So this is going to be the cube root of pi by 2. And this is the cube root of 3 pi by 2. Okay, those x-intercepts. So now we know that we have all the boundaries for our integrals. So here's the integration. We have to integrate x squared cosine x cubed dx. Well, we already knew that from before, so that's 1/3 sine x cubed. And we're evaluating it from 0 to the cube root of pi by 2. So we substitute in the cube root of pi by 2 in for x. Well, the cube root cubed is just going to leave us with pi by 2. Okay, so that's there. And the sine of pi by 2, again, when we look at these, the sine of pi by 2 is 1. So this thing equals sine of pi by 2 equals 1. Multiplied by 1/3 just gives us 1/3. And the sine of 0 is just 0. So this whole thing just disappears. So the blue area is 1/3 square units. When we get to the red area, now the red area is below the x-axis here. So that means that we have to stick on a negative symbol, negative sign in front of the integral sign. And so then we're going to evaluate this integral from the cube root of pi by 2 to the cube root of 3 pi by 2. And we know from before, of course, that the integral of this is 1/3 sine of x cubed. And so conveniently that we've got these cube roots that will get undone by this cube. So then when we substitute in the cube root of 3 pi by 2 here, in for x, we'll just get, and we cube the cube root, we just get 3 pi by 2. So the sine of 3 pi by 2 is actually -1. As we can see over here, this is 3 pi by 2 right here. And so that's -1. So this part is -1, and multiplied by a third gives us -1/3 right here. And sine of pi by 2, as we saw before, was 1. So this gives us 1/3. So we got -1/3 minus a third gives us -2/3, multiplied by the negative out front, which gives us 2/3 square units. And we can see, therefore, that the red area is twice as large as the blue area. Okay, and 17E, question number 3 asks us to take another look at the opening problem in the chapter. And so we've got this intensity of light situation, light intensity entering a greenhouse on some August 8th of some time, some date, some year, sorry about that. So we've got I is 3 sine pi t over 10 units per hour if the day is sunny, and if the day is overcast or cloudy, the intensity is sine pi t over 10 units per hour. So it's 1/3 the intensity as when it's sunny. And the number of hours are the number of hours after sunrise. So we're not sure what time of day the sunrise occurred on August 8th, but at sunrise, it's time 0, and we're going to be looking at the amount of sun in this situation, in this greenhouse, for 10 hours. And so we have our two x-intercepts. That's nice. So the boundaries for our integration. We can identify each curve because, well, we know that from work with transformations that is the a value, which is the vertical stretch. And here we've got a 1 and a vertical stretch of 3. Well, this kind of looks like the C1 looks as though it would, of course, have a more of a vertical stretch than C2. So let's just say that's 3. And right here, that would be 1 to indicate the maxima of both of those curves. And so C1 is going to be the 3 sine pi t over 10. And C2 is just going to be the sine pi t over 10. So we have now identified that. Can we find the shaded area enclosed by C1 and C2? Well, yes, we certainly can. So we're going to take the two curves. So this is now a problem of the area between two curves. Now, back before we began the chapter, we probably couldn't do that, but now we can. So we take our C1, that's the top function or the top graph there, and we subtract the bottom function, and there's 3 sine pi 10 over 10 pi t over 10 here, minus 1 of them here, so that leaves us with 2 sine pi t over 10. Now that angle, that's right here, that angle is can be written as pi over 10 t. So that pi over 10 is actually like the coefficient. So when we integrate sine, we get negative cosine, and then we divide by the coefficient of t. And when you divide by the coefficient of t, you're dividing by pi over 10, and then you flip and multiply because you're multiplying fractions. So the 10 multiplies by this 2, or negative 2, to get negative 20, and the pi goes down below here in the denominator. So 10 times 2 gives us this 20. The integral of sine is negative cosine, because when you differentiate cosine, you get negative sine, and the sine up here is positive. So that's why we have to get that negative here to interact with that negative from the integral of the cosine. And then we just substitute 10 and 0 in. So 10 in, substitute 10 in for t. The 10's cancel, so we're left with cosine of pi. When the 0 goes in for t here, it just gives you the cos of 0. So the cosine of 0 is 1. Cosine of pi, well, if we start like this, cosine of pi is negative 1. So then this here is negative 1. Looks like a 2, that is a 1. So negative 1 times negative 20 over pi is positive 20 over pi. And then, of course, 20 over pi here. So when you add them together, you get 40 over pi units squared. And so if the intensity of light is regarded as the rate of energy transfer, what does that mean? The area in B would mean about the energy entering the greenhouse. So this is actually then the quantity. So if that was the area, or sorry, if the integral was the intensity, the intensity is the rate. So from what we're talking about up here, these intensities are actually rates of energy transfer, then that means that this is the quantity, because the integral of a rate is the quantity of energy. Okay. And so those were all the questions that were requested to see when we were taking up the questions yesterday. And so these are the solutions. Hopefully my explanations of their solutions has helped clarify things a little bit. And hopefully that will help you feel more confident with your work. Okay, so thanks for watching, and we'll see you in class.